To address the question of how planes fly, some background knowledge is needed. As you may know, there are 4 principal forces on a plane: thrust, drag, weight, and lift. If you don't know these, then I don't know. Lift is the most important force because without it, the object would never get off the ground and it wouldn't be called a plane. Lift is found in everything that flies, from a frisbee to paper airplanes. In planes, the lift is generated on the wings. The scientific term is airfoil. There are many different types of airfoils, but we will focus on the 2 most used ones: symmetrical and cambered. Cambered airfoils have a flat bottom and bulbous top. Note that both airfoils have a rounded front and sharp tail. Paper airplanes, for instance, are technically symmetrical airfoils, allowing them to fly. Angle of attack is also important when discussing planes. The angle of attack is the angle that the wing makes against the airflow. So, if the angle of attack is 0 degrees, the wing is going straight into the airfoil. There are 2 explanations for lift generation: Bernoulli's principle and Newton's third law. Bernoulli's principle describes the conservation of energy of a fluid. Since air is a fluid, we apply Bernoulli's equation to air passing over an airfoil. We've learned that the energy can be potential and kinetic. Now we're adding pressure energy into the mix. Pressure energy is denoted as a capital P. With kinematics, potential energy is described as mgh, and kinetic energy is described as 1/2 mv squared. However, because we're dealing with a fluid, we have to change the variables while keeping the thinking the same. Pressure doesn't change, but the mass and height terms do. With fluids, we use density instead of mass. Density is denoted as a lowercase p. Height is replaced with altitude. It is denoted as a y. Here we have one side of the equation, the other side being the same thing with a different subscript. The air going over the top of the airfoil would have an altitude of y2, while the air going under will have an altitude of y1. Since the difference between these altitudes is so small, they're essentially the same, canceling out the potential energy terms in the equation. We can interpret the airfoil and the air around it as a system. Because of this, energy must be conserved. So we can apply Bernoulli's equation. We can make the air passing over the top as one part of the equation, and the air passing under as the other part. In this way, the energy on top equals the energy on bottom. Using a cambered airfoil, we see that the air travels faster over the top than the bottom. But remember, using Bernoulli's equation, energy must be conserved. So if velocity changes in one part of the system, pressure must change also. If the velocity increases as the air does over an airfoil, the pressure must decrease. Additionally, if the velocity decreases as the air does under the airfoil, the pressure must increase. Using this NASA simulation, we can see the effects the angle of attack has on lift. Pay attention to the angle slider in the right-hand side with the lift graph and lift value. As I make the angle greater, air is going faster over the top and slower on the bottom. This creates a greater pressure upward, generating lift. For a symmetrical airfoil, the story is a little bit different. Since air passes at the same speed over both sides, the angle of attack is very important. At an angle of attack of 0, the lift is 0, because there is no pressure gradient. But as I increase the angle of attack, we can see that the lift value actually increases. This makes the air go over the top of the airfoil faster and slower over the bottom. This creates again a net upward force. To sum up the effects of Bernoulli's principle, there is high pressure on the bottom and low pressure on top of the airfoil. Since pressure is nothing more than force per unit area, we can interpret this as a large force upward and a small force downward. This net upward force lifts the airfoil up, generating lift. The second explanation for lift generation is Newton's third law. Newton's third law states that for every action, there is an equal and opposite reaction. In the case of an airfoil, the airfoil forces the air downward with its sharp tail and angle of attack. Thus, the wind reacts by forcing the airfoil up, generating lift. Additionally, the air is given a downward momentum, and to conserve momentum, the airfoil must have an upward momentum. It is important to note that Bernoulli's principle and Newton's third law complement each other and don't contradict. Lift generation is a complex idea, so not one explanation can be right. One of the misconceptions is called the equal transit theory. This theory states that the air going over the top of the airfoil must meet the air going under the airfoil. Because the top has to travel further and meet up at the same time, it travels faster, creating a gradient in pressure. Now, this theory is wrong because there is no reason for why the air must meet up at the end. In fact, looking at the simulations, we see that the air going over the top goes ahead of the air on the bottom, and because of this, the lift generated is much greater than what the theory predicted. The second misconception is the skipping stone theory. This theory states that the air bounces off the bottom of the airfoil, exerting a force upward, lifting the airfoil. However, this doesn't make sense because air passes over both sides of the airfoil. This theory does describe how a space shuttle enters the Earth's atmosphere. However, this is more controlled falling than flight.